So we're going to talk now about polarity in molecules, and we're going to talk both about polarity of bonds as well as the polarity overall of the molecule. Okay, but before we get into that, we need to talk about something called electronegativity. This is going to help us determine polarity. So with electronegativity, it's just going to be the preference of one atom in a chemical bond for electrons. So even though we may be sharing electrons, something's always going to prefer those electrons more so than the other. That's what this electronegativity measures. Okay. Main thing to note with electronegativities, from a periodic table, francium's the lowest, fluorine's the highest value. So fluorine is going to pull electrons more so towards it than francium would. With francium, it's the lower left, fluorine upper right. How do we go from the smallest in the lower left to the largest in the upper right? Well, as we go across a row from left to right, we're going to get an increase in electronegativities. And as we go up a group, we're going to get an increase in electronegativities. So as we go from left to right and then up a group, we're going to be increasing electronegativities. Now that's a general trend. It doesn't hold true absolutely across these things, but in general, that's the way it's going to work. So let's look at bond polarity and thinking about how we can calculate this. We're going to talk something about ionic character. We can have mostly ionic, polar covalent, mostly covalent, nonpolar covalent. Mainly, we're going to call it ionic, polar covalent, or nonpolar covalent. Ionic is going to involve ionic bonds, and that's that transfer, complete transfer of electrons. The covalents are going to be sharing those electrons. Those are going to involve those covalent bonds. Okay, now, these ionic character is going to be based on differences in electronegativities. So if I look at a nonpolar covalent bond, the difference in electronegativities is going to be basically zero, or real close to zero. So things like our diatomic molecules, hydrogen gas, oxygen gas, fluorine gas, the bond between the two hydrogen atoms is going to be a nonpolar covalent. Why? Well, because both hydrogens have the same electronegativity, therefore they're going to be pulling on that bond the same amount. Okay, they're going to share those electrons equally. Okay, that's an example of a nonpolar covalent. Polar covalent, well, you can see the range listed there from a polar covalent is about 0.4 to 1.7. Main thing with polar covalent, if we're dealing with a covalent compound and a covalent bond, and we've got a difference in electronegativities, it's going to be a polar covalent bond. So HF, how do I know that's a covalent bond? Well, hydrogen's a nonmetal, fluorine's a nonmetal. A nonmetal with a nonmetal means I have a covalent compound, which means it's going to involve covalent bonding. How do I know it's polar covalent? Well, because hydrogen and fluorine have different electronegativities. Okay, fluorine's much larger than hydrogen. Okay, when I go to ionic then, that's going to be a difference in electronegativities typically greater than 1.7. Main thing with that, if I have an ionic compound, it's going to involve a metal with a nonmetal. Well, if I have a metal with a nonmetal, that's going to have the greatest differences in electronegativities. Okay? With that ionic compound, the difference is so great that the more electronegative compound doesn't just share unequally, it physically removes that electron from the other. So if I look at sodium chloride, chlorine's got a much larger electronegativity than sodium, so chlorine pulls the electron away from sodium so that sodium becomes Na+, chlorine becomes Cl-. Okay, but it's still based around those electronegativities. Even though there's that table up there that shows the delta En, En being electronegativities, delta meaning change in, or the difference between, there really isn't going to be a sharp distinction between these bonding types. Okay, we will see overlap of some things. Okay, but mainly, if you have a metal with a nonmetal, we already know that's ionic, which means it's going to have a large difference in electronegativities. Ones we're going to be concerned with now is mainly with those covalent compounds. Are we dealing with a polar covalent bond, or are we dealing with a nonpolar covalent bond? So polar covalent, if it's two nonmetals and they have difference in electronegativities, it's going to be polar covalent. If it's a covalent bond, in other words a nonmetal with a nonmetal, but there's no difference in electronegativities, it's going to be a nonpolar covalent. Now, with this then, we have to worry about something called a dipole moment. All right, U represents a dipole moment. It's equal to Q, the charge, times the radius. Main thing with dipole moments, we want to be able to predict these dipole moments. We want to know where we have a positive side and where we have a negative side. That's what dipole means. Okay? Because we have unequal sharing of these electrons, one atom gets a slightly positive charge, one atom gets a slightly negative charge. That's what those Q's represent. It's not a true ion that's formed, not like the ionic compounds. Okay, we're not forming a true ion. This is still a covalent bond. They're sharing electrons, they're just not sharing them equally. So we get this slightly negative, slightly positive side, but we're not forming ions. It's very important to keep in mind. All right, so let's take a look at some examples here. Let's look at just a nitrogen-hydrogen bond. What we're going to do is we want to know which one's going to have a slightly negative end, which one's going to have a slightly positive end, and we're going to represent this direction with an arrow and then some lowercase Greek deltas. If I look at nitrogen and hydrogen, which one has got the greater electronegativity? The one that's got the greater electronegativity is going to pull those electrons in that bond a little bit closer towards it. Well, nitrogen's got the greater electronegativity, so we draw an arrow pointing towards nitrogen. Then we could label that nitrogen end with a lowercase delta negative, and then the hydrogen would be the delta positive, okay, representing a slightly negative and a slightly positive charge. We don't want to just call them positive and negative because that implies they've actually formed ions, and they haven't. Okay, they're just not sharing the electrons equally. Okay, what about a fluorine-nitrogen bond? Which one has the greater electronegativity between those? Well, fluorine does, so the arrow would be pointing towards fluorine. Fluorine would be slightly negative. The nitrogen would be slightly positive. What about ICl? Well, if you look at iodine versus chlorine, chlorine's higher up in the group, so it should have more electronegativity, so this time we draw the arrow the other way, towards the chlorine. And the chlorine would be slightly negative, the iodine would be slightly positive. What this is showing us is this unequal distribution between these shared electrons. Okay, they're not shared equally. Maybe a prettier picture to look at to represent this. We can look at these electron densities here, and we can look at different shapes. We can see a hydrogen-hydrogen contour mapping to show sharing of electrons, and show an FF to show sharing of electrons. When we look at the HF, the fluorine itself has more electrons around it, has a larger density, if you will, than the hydrogen does. So it's an unequal sharing of electrons. Okay, the fluorine has got a slightly negative side, the hydrogen's got a slightly positive side. Another way to represent this, if we look at the pictures down below with the F2, the balls there, each one represents a fluorine. Well, that would be a nonpolar covalent bond. We get equal distribution of electrons within that bond, so everything is green. Okay, if we go to HF, fluorine is more electronegative than hydrogen, so fluorine would be the red side, it's got more electrons around it, and the blue side would be the hydrogen. We've got a slightly negative side on the fluorine, that red, and slightly positive side with the blue. It's still a covalent bond, it's a polar covalent bond because we have that slightly negative, slightly positive side, but they're still sharing those electrons. Okay. Whereas if we go to lithium fluoride, now with these mappings, we're not going to see it completely separate, but we can see further distance between the blue side and the red side. The blue side has moved to the far left of the molecule, the red side has moved to the far right, okay, and they're not overlapping as much in between. Okay, that's for lithium fluoride. Well, that's an ionic compound. So those are just electron densities to show you kind of these overlaps and what's going on. The main thing to recognize is if we've got a polar covalent bond, that means we have a slightly negative end, slightly positive end. Slightly negative end is going to be the atom with the greater electronegativity. Okay, we draw the arrow pointing towards that slightly negative end. Now, what's important? Why is it important to know this? Well, knowing these polarities of these bonds is going to help us predict polarity of molecules, and polarity of these compounds is going to help us predict a lot of different properties. One of which we could look at is example here of, if we look at nitrogen N2, that's a gas at room temperature. H2O, water, is a liquid at room temperature. Well, the mass of N2 is 28 grams per mole. The mass of water is 18 grams per mole. The larger the mass, the more likely it should be a liquid at room temperature. All right. So why isn't water a gas at room temperature? Why is a liquid not a gas? Well, it comes down to this idea of polarity. If I look at a nitrogen molecule and I draw its Lewis structure, I've got N triple bond N. Okay, that's a linear molecule. I've got two nitrogens. That triple bond is a nonpolar covalent bond. So N2 is going to be nonpolar. if I look at water, water's got this bent shape with the oxygen-hydrogen bonds. Well, oxygen's more electronegative than hydrogen, so the hydrogens get a slightly positive end. The oxygen gets a slightly negative end, and that's true for both bonds. Okay, and what that means is when I look at this overall, I get water with a slightly negative end on the oxygen side and a slightly positive end between those two hydrogens. Okay, so overall, water is going to be polar. It has what we call a dipole moment. It's got a negative side and a positive side. Well, because we've got this negative side and positive side, those attractive forces can help hold water molecules together a lot more. And so those water molecules, because they stay together a lot more, they have stronger forces holding them together. They don't want to go into the gas phases easily. So that's one of the reasons why water is a liquid at room temperature and nitrogen is a gas. Nitrogen's nonpolar, water's polar. Okay, so it's important to be able to predict these polarities of the bonds because it's going to lead us to predicting polarities of the molecules themselves. And then that's going to help us predict these different properties that we see macroscopically. Now, before we get into polarity of molecules, though, you've got to understand how to predict these molecular geometries. These geometries are going to be important. If you can't predict these geometries, you're not going to be able to predict whether a compound's polar or nonpolar. Okay, it's going to be vital that you understand how to predict those geometries. All right, so let's look at some examples of these. Let's start with HCl. Well, HCl is a linear molecule, so chlorine is more electronegative than hydrogen, so we draw the arrow towards chlorine. The chlorine is going to be slightly negative, the hydrogen is going to be slightly positive. I've got a negative side and a positive side. It's going to be polar. Okay, let's drop down to BF3. If I look at an individual boron-fluorine bond, fluorine is going to be more electronegative than the boron. So boron within that individual bond, boron is going to be slightly positive, the fluorine is going to be slightly negative. But now, because I have two other fluorines pulling against that boron as well, and I've got symmetry to that because it's trigonal planar, they're all pulling equally away from that boron, and it turns it into a nonpolar molecule. All right. If I think about it, with all of those bonds, all of them have boron as the positive end, right? So I have a positive, slightly positive charge on that boron, which is the center of that molecule. If I look at those fluorines, each fluorine has a slightly negative charge. But if I look at that central location of those fluorines, if I picture those fluorines creating a triangle, where's the center of the triangle? It's right on the boron. So the central location of all of those negative charges is on the boron. Okay, so even though I have polar bonds, it ends up being a nonpolar compound. Okay, that's due to symmetry. That's why it's important to know that molecular shape. All right, let's look at the middle one there, the CCl4. Chlorines are going to be more electronegative, so the chlorines each are slightly negative, the carbon's slightly positive in each bond. Okay, but overall, because of symmetry, because those chlorines are pulling equally in their own directions, it ends up being nonpolar overall because the central location of the negative charge is still on that carbon. Right, let's go to NH3, which is a tetrahedral electron domain geometry, but because it has a lone pair up top, it's going to be trigonal pyramidal. Now we've broken up that symmetry. NH3 is now going to be polar. All right, so when I added that lone pair to the nitrogen, it becomes polar. If I look at CH3Cl, that's a tetrahedral shape, but because one of those atoms is different than the other three, there's not that equal pulling in all the different directions, so it ends up making that polar. Okay, so first we need to identify, do we have polar bonds? Then, depending upon the molecular shape, if it's got symmetry, it's going to determine whether we're going to have a polar versus nonpolar molecule. All right, now, with these polar molecules, we can then predict an overall dipole moment. All right, with the HCl, it's real simple since it's linear. The more electronegative one, the Cl, would be the negative side, the H would be the positive side. All right, with the NH3, the N would be the negative side, the H's would be the slightly positive side. With the CH3Cl, hydrogens would be the positive, towards the chlorine would be the negative. Okay, so those arrows represent the overall dipole moment of the molecule. Not the individual bonds, but the overall dipole moment of the molecule. All right, so when predicting these dipole moments, if you can see the three-dimensional shape and you can recognize whether it's symmetric or not, great. If If you've got a highly symmetric molecule, chances are you're going to have a nonpolar molecule overall. Okay? But the first place we have to start is if a molecule's got polar bonds, it can either be polar or nonpolar. If you don't have polar bonds to begin with, that molecule can't be polar. Right? So if the molecule has all nonpolar bonds, the molecule overall is nonpolar. Okay? And then even with those polar bonds within the molecule, if we have a highly symmetric shape, we're going to cancel out that polarity. Like the trigonal planar. It's highly symmetric shape, cancels out the polarity of those bonds, made the molecule nonpolar. The tetrahedral, same way. Okay? So you need to be able to see those shapes and predict those polarities. Now, what I'm going to show you next is based upon those shapes. If you're having a hard time picturing the shape and predicting polarity that way, knowing the name of the shape that it is, and the types of bonds you're looking at, you can use these next set of rules to predict whether it's going to be polar or nonpolar. All right, so for these general rules, if you have a diatomic molecule, in other words, you got two atoms in your molecule, if you got nonpolar bonds, it's going to be a nonpolar molecule. If you got polar bonds, it's going to be a polar molecule. And once again, keep in mind with all of these, if you have nonpolar bonds and all your bonds are nonpolar, the molecule overall is nonpolar. Okay, that's with all of these listed here. All right, for triatomic molecules, you got three atoms. If it's a linear atom and the two bonds are identical, it's going to be nonpolar. If it's a linear atom and one of the bonds is different, it's going to be polar. If it's a bent shape, it's going to be polar. For tetraatomic, so four atoms. If you've got trigonal pyramidal, it's going to be polar. If you've got trigonal planar and all three bonds are identical, it's going to be nonpolar. If you've got trigonal planar and one or two bonds are different, it's going to be polar. Changing those bonds breaks up that symmetry, which makes it polar. All right, for pentatomic, 5 atoms. If they're all identical bonds and you've got a tetrahedral or a square planar shape, then it's going to be nonpolar. All right, if you got a seesaw shape, it's going to be polar. If you have one or more different bonds, the molecule is going to be polar. All right, for hexatomic molecules, so 6 atoms. If you have identical bonds and you've got a trigonal bipyramidal shape, it's going to be nonpolar. If it's square pyramidal, it's going to be polar. All right, if one or more of the bonds is different, regardless of what it looks like, it's going to be polar. All right, for heptatonic, so 7 atoms. If we've got identical bonds, we're dealing with an octahedral, that's going to be nonpolar. If we've got one or more different bonds, the molecule is going to be polar. Okay, so that covers all of the shapes, and based upon knowing that structure, you can use these rules to predict is it going to be polar or not. So even if you can't see those 3D shapes and see the symmetry and how those things cancel out yet, you can still predict whether it's polar or nonpolar. But you should really focus on trying to understand that concept of symmetry and how those bond polarities are canceling out when we have highly symmetric molecules. And when we break up that symmetry, those bond polarities can't cancel each other out properly. Okay. All right, so let's predict these molecules. Are they going to be polar or nonpolar? So if I look at water and I draw its Lewis structure and determine its electron domain geometry and then its molecular geometry, its electron domain is going to be tetrahedral. Its molecular geometry is going to be bent. I have a polar bond. The OH bond is polar. I have a bent shape, so water is going to be polar. All right, what about CO2? Well, CO2 is going to be a linear electron domain geometry and a linear molecular geometry. C double bond O is polar, but because it's linear, those cancel each other out, so I end up with a nonpolar molecule overall. All right, what about BCl3? Well, with BCl3, I'm going to end in the trigonal planar electron geometry. I'm going to end up with a trigonal planar molecular geometry. Boron-chlorine bonds are polar, but because I have a trigonal planar geometry, those bonds cancel each other out, and I end up with a nonpolar molecule. Right? What about SF4? SF4 is going to start in the trigonal bipyramidal electron domain geometry. Its molecular geometry is going to be the seesaw shape. All right, what about bonds? Well, the sulfur-fluorine bond is going to be a polar bond. Because I have polar bonds, because I have the seesaw shape, means it's going to be polar overall. Okay, so we can use these shapes to predict these polarities. All right, the last thing we're going to look at is predicting dipole moments. So once we know that we have a polar molecule or not, we can then predict what direction that polarity is in so that we know where we have a positive end and a negative end. So if I look at ammonia, I've got polar bonds because it's the trigonal pyramidal shape molecule, so it's going to have this molecular dipole, right? So when I look at this slightly prettier picture here, I end up with a slightly negative side on the nitrogen, slightly positive side on the hydrogen side of things. And that's my overall dipole moment. I know where my negative side is and where my positive side is. I can even do that with the CH3Cl. This is another example. That's a polar molecule. That chlorine has a stronger pull on the electrons than the carbon. Between the carbon hydrogens, the electrons want to move more towards the carbon. Within the molecule, the overall net dipole moment means that we get a slightly negative side towards the chlorine and a slightly positive side towards those hydrogens. And that's how we can predict those dipole moments. Okay, and we just represent those dipole moments with those arrows, and then we put the delta negative for the slightly negative side, delta positive for the slightly positive side for the molecule. All right, but that's going to be it for dealing with polarity of bonds and polarity of molecules.